Purdue University College of Agriculture has a long history of impact in research, education, and cooperative extension to improve agriculture and the role of agriculture in our society. One of the ways that we continue to do that is in this realm of digital agriculture. It's the fusing of our physical and social worlds to make improved data-driven decisions and actions. So you'll see a website up there in the corner. We encourage you to visit that, purdue.ag/digag. I'm Dennis Buckmaster, a professor of agricultural and biological engineering, and I also serve our dean and our associate deans as a Dean's Fellow for Digital Agriculture to coordinate activities in the college, at the university, and through to external stakeholders regarding data-driven, technology-intensive agriculture. One of the projects that we have is the Wabash Heartland Innovation Network. The WHIN project is not exclusively a Purdue project. It is a partnership with WHIN, the organization, the community foundations in a 10-county region of west central Indiana, of course Purdue, as well as Ivy Tech Community College, and many partner organizations, farms, manufacturing firms, etc. The focus of the WHIN project is to increase the role of advanced technology in agriculture and manufacturing. In this series of brief presentations, you're going to learn of how the WHIN funds are being used to advance the technology in agriculture. So whether this particular video covers the capturing, the clustering, the collecting, or the computing, you'll have to wait to see. But in each of these cases, we are moving forward the technology in agriculture through digital means.
Greetings. My name is Dharmendra Saraswat, an associate professor in Agricultural and Biological Engineering Department at Purdue. Due to COVID-19 situation, I am filing a spring progress report on the project titled Evaluating, Developing and Disseminating UAV Sensors and Machine Intelligence-Based Technology for Site-Specific Weed Management from my home. Before I proceed, I would like to acknowledge my project partners, namely Dr. Shreyash Sen from Electrical and Computer Engineering Department and Dr. Bryan Young from Botany and Plant Pathology Department. I would also like to thank my graduate research assistant, Varun Aggarwal, for his research contributions. Last but not the least, I would like to thank Wabash Heartland Innovation Network, in short WHIN, for their funding support to make this project possible. There are 4 major project objectives. Objective number 1 is about evaluating deep learning algorithms and selecting the ones with high accuracy in identifying weeds. Whereas the objective number 2 is to generate data sets that could be used for satisfying the objective 1. The objective number 3 is about identifying computers that meet certain design criteria, then integrate those with UAVs so that the UAVs can be used for real-time weed identification purposes. And the last objective is about educational outreach so that we can disseminate project findings by conducting workshops in counties represented by WHIN. A number of deep learning algorithms for image classification and image segmentation are being tried as part of Objective 1. Image classification algorithms will provide us a general sense of crop health related information from the field image, whereas image segmentation will be applied to those parts of the field image where a higher weed density is expected so that we can pinpoint weed type and its location in order to implement site-specific weed management measures. Of course, image segmentation gives us more information about the scene. It comes at a price. It requires more computational power and usually about 5 to 6 times slower compared to image classification. 3 deep learning classification algorithms were tested on publicly available database comprising of 453 images to classify 4 weed species, namely cocklebur, foxtail, giant ragweed, and red root pigweed. About 60% of the images in the database were used for training, and almost 20% each were used for validation and testing of the 3 classification algorithms. Despite using a small size of database, the accuracy values obtained from image classification algorithms were very promising and ranged anywhere from 85 to 99%. Another publicly available dataset was used for evaluating the performance of image segmentation algorithms, and the image dataset had 3 different objects: the sugarcane crop, presence of weeds, and soil. The overall accuracy of segmenting sugarcane crop, weed, and soil was approximately 96% after 300 epochs of training. So we are very pleased with the performance of the algorithms that we have selected for image classification and image segmentation so far. Please recall that the objective number 2 pertains to generating data set that can be used for training image classification and image segmentation algorithms. To enable field data collection using a UAS, Varun, my GRA, has already obtained a remote pilot certificate, and this would allow him to collect field data by flying over experimental fields at various heights, speed, and time of the day. And in addition, an image acquisition platform has also been developed for acquiring images in a greenhouse setting. Objective 3 is about identifying various computing platforms. The design requirements for the computing platform include that it should be power efficient, it should have high computational capabilities, it should be lightweight so that it can be carried over an unmanned aircraft system, it should be flexible to changes during flight operation, and it should also have the capability of real-time data processing. So for this purpose, we have identified 2 different setups. Those setups have been bought, and we look forward to testing them during summer 2020. Objective 4 is about educational outreach. Since we are at a preliminary stage of data collection, we look forward to reporting on this objective in weeks and months to come. Thanks for listening to this presentation. If you have any questions, please send it to the email given on the slide.
Dharmendra, thanks very much for that update on the work that you're doing related to the weed identification, classification, and control. I did have a question about that image that you had with the weed classification. What would have been the maturity of the weeds at that time?
I would say that just by looking at the pictures, they were small size weeds that we typically see during the early seasons in corn and soybean crops.
Okay, great. You mentioned that part of your work is going to be to generate data for yourself, of course, and maybe even releasing for others to do similar work.
Yes.
Do you have a guess? Will that help draw businesses to this region, West Central Indiana, connecting them to Purdue?
Yes, we always hope that that is what is going to happen. And let me also give you a little bit of brief background as to why we built a setup to really generate database from different perspectives. in the field of deep learning and convolution neural networks, it is not uncommon to hear that we can generate synthetic images at different angles, and then that's how we can augment the existing databases. However, I did not come across any study where they compared that how that would compare with the real life weed images that we captured from different perspectives. So that's why we have built that setup, which will allow us to capture the same weed at different growth stages from different angles, and then probably we will generate a synthetic database using one leaf from one perspective and see that how it compares with the real life data set. And then if time permits, we would like to capture at least the same weed from a couple of angles in the real field conditions. And that way we want to really have a good set of databases that other researchers may also find useful, and that would give them an opportunity to really come and look for the data set that we will be hosting on Purdue resources.
I think you captured it nicely, because this data is complex, and the more dimensions you have, not like XYZ dimensions, but the more angles and perspectives that you can provide, I think, yes, it's a more robust data set. So. And my last question is, you mentioned in the computing pipeline putting your processor on board your UAV, UAS. So you would be carrying the computer up with the imaging cameras, or were you considering the pipeline to bring the data down to the ground?
Oh, in fact, we are planning to integrate everything with the UAV or UAS itself.
Okay.
So, that's why the power requirement and the weight of the unit and the processing capacity, all three factors were very, very important. And we think at this point of time that we have a very, very good solution available to us. And right now, we are testing it out to see that how far we can run with it.
Okay, sounds great. I'm optimistic.
Thank you.
Yeah. Well, thanks again for the update. Really appreciate learning about what you're doing.
Thanks a lot, and I appreciate the support from WHIN and the support that I'm getting from you and the Director Extension. So thank you very much for doing that.
You're very welcome.